Hello. Now we will study the free expansion. First of all, we'll understand how this free expansion is different than the normal processes. And then we will make the formulas for this free expansion for work done by the gas and heat given to the process. Okay. So first, for the differentiation. Now, let's say this is a chamber. This is a chamber, and in the chamber, this is a divider. There are two chambers, A and B. In chamber A, there is a gas A. There are n number of moles of gas A, and these moles of the gases, these atoms of the gases, they are moving. And in chamber B, there is vacuum. There is nothing there in chamber B. And there is this divider, or you can say it's a piston sort of a structure. Okay. So now these gas molecules, they will keep moving, and continuously when they will keep moving, they will collide with the walls of the chamber. And this divider included. These atoms will also strike with the divider. So in this process, the striking process, they will impart a force which we calculate in terms of pressure. Okay. So in the normal processes, the processes we have studied till now, what used to happen, the volume change used to happen by the movement of the piston. This piston used to move, or the boundary used to expand. So this is our system for the gas A. So the boundary of the system used to expand. And the cause behind that used to be the collision. Obviously, if the boundary is expanding, some force is required. And the force comes from the collision. These atoms, they keep colliding with the walls. And in this process, they apply the pressure force. And through that force, they move the walls. So when the walls are moving, the volume changes. And because of that, we always find that dWg is non-zero whenever volume changes. And when we calculate this value, it comes out to be PdV, if you remember that. Okay. This is the normal process. When the boundary is changing, when the volume is changing, expanding, compressing, both things are possible there. Okay. Now let's talk about a different phenomena, meaning volume is changing, but this time this volume starts changing because of some leakage. So what if there is nothing, there is only vacuum here. What if I create a leakage here, a hole? If I create a hole, what is going to happen? This gas A, which is in the chamber 1, will move into the chamber B. And in this process, this gas will acquire the more volume. The volume available for the gas will increase, or I should say the delta V value will increase. So from that logic, from this formula, since the volume is increasing, there have to be some non-zero work done. But there is a problem there. Meaning I can make a hole, or I can completely remove this divider also. If I completely remove this divider, not in this direction, but immediately if I completely remove this divider, what will happen? Suddenly, the gas will find the extra volume to occupy. And in PV is equals to nRT, V is the available volume for the gas to move. So earlier the gas was moving in this volume only, now it will move in complete volume. Whether I create a hole or I completely remove the divider. So with this process, when the movement of piston is not happening, the elimination of piston sort of a thing is happening. In this case, the volume available for the gas is increasing. Delta V is still non-zero. But when you calculate the work done by gas, that comes out to be zero. So work done by gas, in case of movement of piston, this is for movement of piston, or you can say that movement of boundaries, is non-zero. When the volume is changing with the movement of piston or with the movement of boundaries, the work done by the gas comes out to be non-zero. But when the volume changes, meaning delta V is non-zero here, volume is changing, but not due to the movement of piston, but elimination of piston. Elimination of piston or elimination of boundary. So due to something, suddenly the volume increases without the resistance. So the volume available for the gas, here also it is non-zero, but when you calculate the work done, it comes out to be zero. What is the reason behind that? Let's talk on to that. The thing is, if you talk about gas, there can be two types of forces which can act onto the gas. One are the forces which are applied by the other gaseous particles, and other are the forces which will be applied by the boundaries of the system. Okay. So since it is an ideal gas, so for the ideal gas, the forces applied, internal forces applied between the ideal gas particles is always zero. So if I talk about the total gas, if I talk about the work done by gas, and that too total. It can be the summation of internal plus work done by the gas onto the boundary of the system. So these two works are possible there. Okay. This is 0 because we have already assumed the ideal gas. We only work with ideal gas. This value, this work done will be non-zero only if the boundary, if the volume change is happening due to the change in boundary. Okay. So when the volume change is happening due to the change in boundary, which used to happen in the previous processes, the total work done by the gas will come out to be non-zero. But when it is not happening due to the change in boundary, and this work done is already 0. So if it is happening due to the elimination of boundary, sudden elimination of boundary, this work done, though the volume is changing, but still there is no force applied, there is no force applied onto the boundary. Boundary is suddenly eliminated. So the atoms, they don't have to do any work there. They don't have to do any work in expanding the boundaries. They don't have to do any work. So when they don't have to do any work in expanding the boundary because the boundary is suddenly eliminated, the work done by the gaseous particle, total work done by the gaseous particle will be 0 there. Okay. So that's the concept behind that. So in case of free expansion, what happens? The boundary suddenly vanishes. When the boundary suddenly vanishes, the work done by gas will always be 0. There is only one condition there. The gas has to be ideal for ideal gas. Because if it is not ideal gas, then there might be an internal work done. Okay. So if work done by the gas is 0 there, so there is this system. There is this system. So obviously first law of thermodynamics is always valid. First law of thermodynamics is always valid. So there might be some transfer of heat to the system. There might be some transfer of heat to the system. Corresponding to that transfer of heat, there is some work done and remaining part used for change in internal energy. Okay. So from first law, if you see, it is dq is du plus dwg, meaning I am applying the first law for free expansion. And we understood how the free expansion will be happening. So dwg is 0. It is 0 for free expansion. Now we know that. It is 0 for free expansion. So we'll have dq is equals to du. Whatever heat will be given to the system from outside, that heat will be utilized to change the internal energy of the system. And we know how to calculate the internal energy. That is NCVDT. NCVT. Okay. So we can calculate how much internal energy change is happening. Now if my system is such that, or if my process is very fast, if process is very fast, meaning if suddenly the change in volume is happening very sudden, very fast, or this boundary of the system is insulated boundary or insulated boundary. By insulated boundary, we say there is no heat transfer happening between the system and surrounding. So if it is an insulated boundary or the process is very fast, in that case we can say dq is 0. And if the dq is 0, du is also 0 because you see here. So we can say u initial will be equals to u final. So initial internal energy of the system and the final internal energy of the system will be same, but only when either process is very fast or this boundary is insulated, meaning in different words, the examiner is telling you that dq is 0. If that's the case, in that case, whatever was the internal energy initially, that will be the same internal energy finally also. Okay. So one more time, let's explain this whole phenomena. Free expansion, first of all, we have to learn how it is different than the previous processes. In case of previous processes, in both the processes, the volume changes. The system's volume changes. To change the volume of the system, there are two ways. One way, we can move the boundary or the piston with the movement of piston. If the movement of piston is happening, in that case, work done, if delta V is non-zero, in that case, work done by the gas is also non-zero. Okay, and that's we calculate by PdV. But if the volume change is happening, not because of movement of piston, but because of elimination of piston or because of some hole created in the boundary, because of which the gas will be going out or moving into different chambers, in that case, it is a free expansion. Though the volume is changing, but there is no work has to be done by the gaseous particle. There, the total work done by the gaseous particle we define as the internal work done against other particle, which is always 0 for ideal gases, or the work done against the movement of system's boundary. And because of that, in case of free expansion, work done by the gas is always 0. Only one condition, it has to be ideal gas, because if it is not ideal gas, if it is a real gas, in that case, internal work done will not be 0. Okay, but this work done will always be 0. So we can also apply the first law. If we apply the first law for free expansion, dWg is always 0, dq will be equals to du. And if the process, this is the condition basically, this becomes a formula. Whatever heat you are giving to the system, that will be converted into the change in internal energy. But if there is no heat transfer to the system, that will be happening if the process is very fast or the walls of the system is insulated. Then dq will always be, also be 0. In that case, initial internal energy and the final internal energy of the system will be same. Okay. So this is your free expansion. Thank you.